Hi, this is TheoryStation, and I'm John Duggan. This program is called Rational Choice Modeling. The series we're in is called the Basic Formal Theory Toolkit, and this is the second installment in the series. In the first installment, I talked about mathematical modeling in general. I gave my schematic diagram for the modeling enterprise, and then we talked about like the most basic rational choice model you have, which is the model of preference and choice. What I want to do here is return to that basic model. And I just want to push it in a couple different directions. So to remind you, we started off with a set of conceivable choices. And a list of preferences. And then we had this little running example where we had 5 conceivable choices, just labeled A, B, C, D, and E. And in this example, the decision maker's preferences, well, the easiest way to represent those was just by ranking A at the top, and then, B and C, and then D and E tied at the bottom. When all of those conceivable choices were available, we applied the optimality principle, and we noted that, well, the best thing this person can choose is A. And that model gave us a prediction. I should say it could also be used normatively to say that this person should choose A. At any rate, that was the basic model. And well, there's different ways to push this. One way of pushing it would be to suppose that not all conceivable choices are available to the decision maker. So what are the available alternatives? We're going to have another set let's call it capital Y. These are the choices that are available to the decision maker, and sometimes this is called the feasible set. Technically, it's going to be a subset of X. And over here in our example, you could imagine that it's, let's say A is no longer available, but B and let's say D and E are available. So, so A and C have been deleted from the set of possible choices for this decision maker. In that case, in blue, those are the set. That's the set of possible choices. If you want to think about A, B, C, D, and E as possible candy bars, this guy goes to the vending machine and finds out, oh, 2 of the candy bars are out, so there's only 3 left. Or if these are candidates in an election, maybe 2 of the candidates dropped out. So at any rate, obviously the decision maker would still like to choose A, but it's not available. So our optimality principle, we can still apply it. And again, in words, what it would be is that the decision maker chooses the best thing that they can. That is, they'll choose the best alternative that's available. In this case, instead of choosing A, which is not feasible, the decision maker would choose, well, either B, D, or E, but obviously B is preferred to D and E. And so the decision maker's choice goes from A to B. So this is a more general model, but and it allows us to think about some choices that are not actually available. Something that we can do in this model that we couldn't do before is see what happens to this person's choices as we change the feasible set. Okay, so that exercise is called comparative statics. We're changing some elements of the model and seeing what happens to the predictions or prescriptions that come out of it. And in our running example, if we go back to that, you can imagine a new set of available choices. And let me put this prime symbol next to our y. So that's a new feasible set. And suppose that is just B and E. So basically D. Now we're thinking about a hypothetical where D is no longer available. All right, so the feasible set goes from this blue to the red, and we can apply the optimality principle again. What happens to this person's choice? Oh, actually, nothing happens. So that's kind of a boring comparative static. But that's actually illustrating a more general principle that you see not just in this really simple model, but in really any model of rational choice. If a decision maker is making some choice that's feasible, it's the best thing that they can choose, and then some other options become unavailable, well, that first thing that you were choosing, it's still going to be the best that you can get, right? So there's no reason to change that choice, right? If you're choosing something the best you can, and then something worse drops out, there's no need to change your mind. All right, so let's go on from, I know. So let me mention another way of representing preferences here. So in the last installment, I wrote out the list of preferences, and that was really cumbersome. And we decided, okay, it's much better to use a ranking. But what if instead of this simple example, suppose that we have instead of 5 alternatives, suppose we have 100. I don't want to write a ranking down with 100 different things in it. So what we can do is we can just say, instead of writing the ranking down, we can just say, okay, there's some list P, and given possible choices or alternatives X and Y, we can say, we can write XPY if X is preferred to Y. So I'll say if the list contains the preference X to Y. This notation, this XPY, here we're using P as a binary relation, but let's just keep that notation in mind. So if I write XPY, it just means the decision maker prefers X to Y. Let me, and that way I don't need to write out every alternative in a person's ranking. I can just use this relation notation. Let me build on this a little bit and describe the idea of a utility function. So a utility function is it's going to basically assign a number to each alternative in our set X. Okay. if we have 5 alternatives, well, maybe that's A, B, C, D, and E, we're just going to assign a number to each alternative, and I'm not going to get too fancy here, but so these utilities, as we call them, these numbers, are going to be on the read line somewhere, and then we're just going to assign higher numbers to alternatives that are better. So, for example, so we might assign A the number 5, B gets the number 4, C also gets the number 4, and E gets 1, and D also gets 1. Okay, so this is an assignment of numbers to each conceivable alternative. Again, the rule is that we have to assign higher numbers to alternatives that are better. Here you can see that A has the highest number. It has a utility, we say a utility of 5. And I can write this out in a table. B, it's not as good as A because it has a lower number. We're assigning it the number 4. C as well is assigned the number 4. And then D and E are assigned the number 1. Now, so you can see that A is the best alternative given the utility function that I'm assigning, the utilities I'm assigning here. B and C are the next best alternatives, and right, because they get a 4 instead of a 5. D and E would be the worst alternatives given this assignment of utilities. So in fact, I'm really just describing the ranking from our example, right? A at the top, then B and C below that, and then D and E at the bottom. But instead of writing down a ranking, I'm assigning numbers to alternatives. Okay. So the left-hand column here is the alternative, and the right-hand column is the utility I'm assigning to the alternative. Okay. In general, the utility assigned to X is written, I'm going to use this functional notation, but instead of an F, I'm going to use a U, because it sounds like utility. And the requirement is that we assign higher numbers to better alternatives. And the way we would write that formally is we would say, for all alternatives, X and Y, if X is preferred to Y, then it should have a higher number. And I'll use this logical notation. That means if X is preferred to Y, then it has a higher number. But actually, the other direction has to hold too. So any alternative with a higher number is preferred. So this is called if and only if, or the logical biconditional. Okay, so a utility function, again, is just an assignment of numbers to alternatives where a higher number means the alternative is better than something with a lower number. All right, so so with this apparatus of a utility function, The optimality principle that we talked about before that just becomes the idea of utility maximization. Right? If you think about it, choosing the best alternative that's available to you would be the same thing as just choosing the alternative that's available with the highest utility. Okay, and so this, when we talk about rational choice, we talk about maximization. That's what we have in mind, is maximizing utility, but it's just one way of describing the optimality principle. Okay. All right. So we've extended this basic model of preference and choice and introduced some concepts. In the next installment, I want to, we're always going to be using this preference and choice model, but we're going to elaborate on it in different ways. In the next installment, we'll talk about cost-benefit analysis, which is a special case of this, actually.